So I will invite Dr. Das up again to do the introduction for Dr.
Dr. Calum McRae is a professor of medicine at Harvard Medical School and vice chair for scientific innovation in the Department of Medicine, Brigham and Women's Hospital. He's the principal faculty member at the Harvard Stem Cell Institute, an associate member of the Broad Institute of Harvard and MIT, and a cardiologist and geneticist specializing in inherited cardiovascular disease. Dr. McRae believes medicine must move beyond static snapshots of health towards continuous, individualized measurements that enables earlier detection of disease and more precise intervention. His research focuses on integrated genomics, deep phenotyping, and medical health technologies to better understand disease mechanisms at the level of the individual. He's a director of the One Brave Idea, an $85 million transdisciplinary research program funded by the American Heart Association, Verily Life Sciences, and AstraZeneca, which has redefined coronary heart disease by identifying novel biological pathways and developing new approaches to multidimensional health measurement. He also serves as the PI of the Apple Heart and Movement Study, Apple Health Study, and a large research collaboration with Samsung Inc., integrating wearable technology with genomic discovery. Across his efforts, his team has developed systematic methods to link basic biology with real-world clinical data, accelerating translation from discovery to care. He's authored more than 160 peer-reviewed publications, holds multiple patents, and has received sustained funding from the NIH. In addition to his academic leadership, he co-founded Tenas and Advan Health to advance scalable precision medicine and automated care delivery. Please join me in welcoming Dr. Calum McRae.
So thank you very much for that kind introduction. You'll see in a minute or two that I am not an expert in frailty. But have been working in reserve quite considerable distance upstream of the traditional evaluation of frailty. You'll also realize that I am quite frail since I was up most of the night doing patient care, so I may not be as robust as I might seem. The title I was given was New Frontiers in Measuring Functional Reserve, and I'm going to try and address that in the context of frailty that has been so beautifully outlined by the speakers earlier today. Some disclosures, as mentioned, 4 companies, 2 of which I founded, 2 of which have licensed technology from us, all of the funders on the left, and then obviously the most important thing, which is the thing you can't measure, which is academic self-interest. And that actually is a theme that we're going to go back to, is that the fundamental problem in almost all of these areas of health, wellness, frailty, and robustness is the lack of any active measurement until after the events have usually taken place. I'm going to briefly outline my talk, a general evolution to multidimensional frailty or resilience, talk about the scales and concepts, scales and data supporting different concepts in different settings, some of the challenges with existing metrics, which you've already heard about, so I'll skip through that pretty quickly, a proposed framework for multidimensional reserve tools, and essentially what you'll hear about is generalizable perturbation response couples. And ultimately, as I've said a couple of times at the table, the only real things that allow you to do that are physics, chemistry, and time. Talk about the contribution of digital tools in this overall setting. Talk about user factors, which, as Megan said, are really an important piece of this. And then think about how we connect this layer of digital technology to some of the biology that we have alluded to during the course of the day. I don't want to reframe anything, but just to say these are hugely expensive problems. You can see here susceptibility to injury leads to about $200 billion worth of lost work. And in fact, one of the ways that we got into this early was actually looking at days off work. That's one of the fundamental things that I think is worth thinking about in anything that we do, particularly in the current funding environment, is how do you get funding to actually do what you need to do in order to show that it's worthwhile for regulated populations. One of the ways to do it is in unregulated populations. And as Megan and Dave both said, there are huge all-cause mortality effects are evident at the end of this trail. However, the frailty and clinical outcomes literature is somewhat fraught, I think, because Although there are multiple clinical studies, they're typically very heterogeneous in their outcomes. They often have limited cross-context validation. And part of the problem is that many of them are actually surgical studies when the first evaluation of the patient was the day after they were admitted. The reality is in most of these, there's still a very good correlation between frailty and outcomes. But it gets at the fundamental problem, which is highly heterogeneous vulnerability, highly heterogeneous stressors. How do you begin to understand what truly is the background that is placing these individuals at risk? There's some great evidence for reversibility and frailty not. There are a couple of very small studies in very elderly frail cohorts, now most recently in heart failure with preserved ejection fraction and in prehabilitation before surgery. But these are almost all somewhat skewed from the traditional data sets that we've been talking about because they're often elective in order to actually do anything ad hoc. Here, however, it is worth pointing out, despite these are small studies, effect sizes are quite large, and there are dose-dependent results. I do genuinely believe them, and I'm nowhere near as much of an expert as Day and Megan are on these topics, so would love their input on this, perhaps in the panel. The way I've looked at almost everything I've done in the last 25 years is that systems approach is a really great way of addressing complexity. One of the nice things about AI is it allows you to do this at massive scale in almost everything in our day-to-day lives. The core element of every systems analysis is perturbation response. How do you understand if a system is robust, whether it's a bridge or a building? You actually have to test it, or a person. You have to test it and understand how it will respond to a variety of different stressors. And in fact, one of the problems is I think we know very well how people respond to a small subset of stressors. We've absolutely no idea how they respond to unknown stressors. And in fact, one of the things many in the room will have experienced is the stress of COVID. So one of the things that became clear to me during COVID was that people between the ages of 22 and 30 were unbelievably emotionally stressed by being isolated for 4 years. And that would not even have been on my radar as an index of frailty had I not been doing the Apple Heart and Movement study and was monitoring general anxiety, depression scales, all of these on a weekly basis through 200,000 people. And so one of the things that I think we have to ask ourselves is, how do we avoid boxing ourselves into legacy frameworks? How people have measured things for the last 20, 30, 40, even 100 years. And it's not in any way restricted to frailty, it's endemic in all of biomedicine, is we tend to just think about digitizing the 18th century instead of asking ourselves, how can we collect stuff from wherever it is, at however low a cost ideally we can make it, that informs everybody about their futures. And one of the nice things about this type of approach is it can technically be quite black box and still be quite useful if you're actually annotating it properly with the right perturbations. So you don't even need to know how a system works. And I can assure you, having spent decades working on the biology of one gene that we discovered about 25 years ago for atrial fibrillation, and we know nothing about it. Everything is connected to everything else. I stopped counting after we found 23 mechanisms by which this gene could cause atrial fibrillation. So what we need to think about in biology and medicine, to be honest, in most of science, it's already the case, but very, very weakly done in medicine. Both the earlier speakers alluded to it, is deal with the fact that there are vastly more unknown unknowns than are known unknowns. So don't do anything that has legacy content because you're going to miss stuff, because guess what? Most of the stuff is not in the legacy content. And then build this in a way that is generalizable. That's actually the metric of science. And one of the things I've noticed in biology over the last 30 years is people like to build things that are bespoke for their own little environment. And what you really want to do is build something that will work wherever you are and predict something that's of utility for whoever uses it. And so there are probably only 3 things that actually have that type of rigor. Mendelian genetics, chemical screens, so it's a small molecule, operates at every single level. And then interventional trials, the true randomized control trial. And these are very difficult to do when things are so heterogeneous. Frailty and resilience is no different. I think the ideals we want are inputs that are based on information content, not just the task in hand, not just what we have available. Actually map information content, understand what overlaps and what doesn't overlap. One of the biggest problems with almost everything in medicine is it's completely correlated with everything else that we measure. And so heart rate variability basically predicts almost everything, but as a result predicts almost nothing. Move from retrospective or cross-sectional studies to continuous personal data. And I'll talk about that in some detail. Look at things that have wide dynamic range so you're not essentially confining and conflating signal and noise. And so in order to do that, one of the nice things is what you want to do is basically build a huge portfolio of things you can measure and pick the ones that are most informative based on actual data, empiric solutions. And then finally, and I think as Megan certainly highlighted, understanding mechanisms helps you then get to interventions, whether they're exercise, nutrition, or pharmacology. And I think one of the core problems with the way that frailty has ended up being framed, not as a result of anything from the people in the field, but the way it's perceived, is that it's after an event. And so people think that there's no possible way that that could in any way be mechanistically understood in a way that you could build a drug for it. And I was excited to hear that Megan is working to do exactly this. But ultimately, I'm not going to reframe everything that Daya and Megan said, but the real concept is, why are we not measuring reserve in every single domain that we have access to? Our ability to get on a bus, our ability to log into our laptops, which varies day to day depending on how we feel, how much sleep we had the night before. These are the types of things that actually will help us build new frameworks that are informative not just for frailty, but for almost everything you can imagine. So we need an efficient collection of individual data at massive scale. I mean, one of the things that we forget, I once looked at the stack that Uber has, and they basically told me when I visited that they have not seen an inflection from artificial intelligence till they had 100 million transactions a day. And if you think about the things that we do in medicine, we're always stuck in this situation where we're operating, almost the research is in a separate space. What we actually need is to integrate all of this into everything that we do and collect. And anybody in the room who was admitted or seen in a hospital or seen in a clinic during COVID probably thinks that all of their information was captured and stored and analyzed. But the reality is, out of the 1.5 billion people who had COVID, same disease, last 3 weeks, same single perturbation, only 10,000 people worldwide had their data collected systematically. And that's the basic problem. We throw away most of the data. Integration of multiple domains, which are known and ready to contribute. I'm not going to go through these again. Data on reserves and dynamics over time, ideally longitudinal trajectories, and then data on the scope of reversibility. So about 8 years ago now, I was funded to actually begin to measure wellness. The project was, as was mentioned, funded by Google, Verily Life Sciences, AstraZeneca, the AHA, and we also had additional funding from Quest. And one of the nice things about it was we were able to take things that typically look like they are actually risk factors, but they're really, the disease is already there. 100% of people who are diabetic have coronary disease on the day that they're diagnosed in most of the large epidemiology studies. Yet we still in medicine think of diabetes as a risk factor for coronary disease. Everybody who's got diabetes, the day they get it, has already had about 25 years worth of coronary disease. So can we begin to move much, much earlier to get at disease processes before they become final common pathways? And that was essentially what we ended up trying to do. So we stepped back and said, what can we think about that will allow us to collect new and informative phenotypes, the focus in human biology? Ideally, we'll want an unbiased reanalysis of existing data types. So one on the top here is bioage from a single lead ECG. You can very easily map somebody's chronological and biological age and look at the difference. And this is actually a particularly good index of frailty. It turns out almost any metric of chronological age compared with biological age actually has a very good predictive utility. We wanted to look at evoked phenotypes. So this is the stimulus that I'm talking about, chemistry, physics, or time. Nutrition, environment, microbiome, drugs. Think of how many people in the audience have had a drug. Almost everybody has had something by the time they're about 15. And yet we never measure the response. And that response actually turns out to probably be the single most precisely characterizable biological feature that you will ever have in your life, because it's a small molecule whose exact mechanism is understood to a level of resolution that almost no other stimulus is really thought of. And then think about consumer data exhaust, and we'll talk about all of these, as well as continuous or semi-continuous passive collection of other data in a robust enough fashion to be able to vertically integrate it. And wearables, as you might imagine, check all of these boxes, but they're not the only thing. So there's been a few studies, wearables in frailty, heard some of them from Megan. they're often, and this is not in any way a slight of these studies, quite the opposite. This is how studies tend to get done because people are coming at the problem from the standard medical model. And what I'm trying to have everybody in the room think about is, how would you come at this if you were starting from scratch and there wasn't any medicine? How would you actually rebuild things so that it did what you wanted it to do instead of trying to bolt something onto what already existed? I told you I was tired. Much of the results, much of the work that's been done in this space is defined by bespoke devices, and these may be incredibly effective, particularly if they have information that is not shared with some other neighboring device. But what tends to happen is everybody builds the same device. Everybody builds something. I mean, if I had a nickel for every time somebody's asked me to measure heart rate variability with a new device, I would be a very rich man. There often are, and again, not through anything other than the existing literature and the existing biases in the field, they're often based on musculoskeletal endpoints. I told you a minute ago that 22-year-olds have psychological endpoints, not musculoskeletal endpoints. But guess what? Those two interact directly, particularly when you're 85 or 90, particularly when you haven't had any sleep. They're often small study sizes, and they often have very specific indications. Again, another thing that we tend to do is make point predictions. So we see something at a T0, and we try and predict something that's going to happen in the next 30 days. That's something that which almost any predictive tool is very, very bad at doing. What you really want is something that's convergent on an outcome that you're really interested in, and have a panel of things that allow you to actually map over time where somebody is headed, and then that allows you to intervene. And then often we measure failure, which is frailty, as has been beautifully outlined already by Dave and Megan, but we don't measure reserve because we don't have any data on reserve because it's already broken by the time we actually see the individual. And so we actually started working with, this is work that's done by Bruce Levy at the Brigham, just asking ourselves, can we even differentiate the different types of admission with things that are not really necessarily even frailty metrics, but just elements of how somebody's getting short of breath. Are they panicky? Do they have chronic lung disease? Do they have pneumonia? Do they have heart failure? And again, you can see this was a very small study, but even with just a simple phone with a reasonably robust training set, you can begin to dissect whether somebody has pneumonia or heart failure. And more importantly, you can then port that to the community. And I'm going to go through several of these just quickly to give you a sense of where it is, partly because much of what we're doing is actually still in the process of being completed. But I'll show you some of the challenges as well. So this was a study we started doing about 4 years ago, where we thought we'd look at the hospital work population. It was greater than 18 years old, but the average person that we looked at was about 58 years old. And we're looking at the staff at Brigham and Women's Hospital and seeing if we could predict days off work. And we did this really as an initial pilot to try and understand what are the factors that allow people to participate in the study or not, what's actually going to be feasible for us to do going forward with a healthy group. And you can see we set out flyers, we had interest in enrollment, we had a whole questionnaire to start with. We had only a 2-week study period. And then at the end of study, we had the watch coming back. And I thought it was effectively really just testing the metrics. And we only had at the end of the day, about 50 people in the study. But what we were trying to do is understand where are we going to go wrong? Where are we going to meet barriers if we start to do this in elderly populations? So exactly as I would have anticipated, what we saw was there was huge subject-specific variation day to day. So everybody had a different normal range depending on what day of the week it was, because we weren't actually collecting the right metadata. We didn't know what they were doing. We couldn't possibly know what they were doing. There were a very wide range of measurements over the study period. Most of the parameters that we measured, all of which are standard physiologic parameters from a watch, I should have listed those. They're on the back here. So it's PPG, IBI, heart rate, accelerometry, sleep onset and offset. It's a fairly modest set of parameters, but they all had so much distributional drift because people were on shift work. We actually deliberately included people on shift work because we thought that might be one of the ways that we could study some of the resilience. We needed much more context. And in fact, one of the things that we found was that almost none of the physiologic data were reproducible for that individual unless you recorded them in deep sleep between 1 a.m. and 4 a.m. So immediately, all of the rest of the collection was essentially virtually uninterpretable unless you had that anchoring measurement between 1 a.m. and 4 a.m. So what you can see this in the panel, wide distributions all the way through the day. And then suddenly, when you start to look at nighttime distribution, you can very quickly narrow the scope of that and get a really good sense of what somebody's personal physiologic range might be. I'm coming back to this because we're going to see this come through the next couple of slides. But one of the things I've said this probably in a different way each time, that you can see is there's this huge gap through wellness and preventative pre-disease into traditional healthcare. There are very few things that we understand before you show up in the hospital or in a clinic. And almost everything that we're measuring, almost everything that we have in the record is after somebody has presented. So how can we go back and understand disease before it happens or redefine disease based on its origins? So one of the things that was quite interesting in this was that one of the best additions to all of this was the passive metadata. We were able to show, this figure did not unfortunately transmit, there's actually a very, very good correlation between resilience and literally on any of the core metrics and the heart rate variability between 1 a.m. and 4 a.m. No correlation with any other timeline. There was substantial inter-individual and intra-individual correlation between almost all the metrics that we measured. So we had all that list of 7 metrics, but they were all correlated with each other. So the information content per unit cost was actually relatively modest. And then the other thing that was interesting was we were able, with only 50 individuals, to begin to build completely unsupervised states. And you can't see this down at the bottom, but we could actually identify what type of physiologic state anybody was in without any supervision of learning. The models are very easy to create because the physiology changes over time as soon as you have the right metadata. This is just an example of sleep patterns. This was actually reproduced in about 200,000 individuals in the Apple Heart and Movement study. But you can actually see that some people have very, very little variation in their sleep duration throughout the whole of the month. And other people are wildly, plus or minus 4 or 5 hours different on a night-by-night basis. And so you can imagine if you don't have any organizing metadata, you're in serious trouble. There's some really interesting data that you can capture from orthogonal information. We used auditory evoked responses while people were checking in at an echo clinic to identify a subtype of heart failure. A near-infrared camera photographing people getting up to go into the echocardiographic suite was able to identify the difference between genetic and ischemic types of heart failure. And then there are all sorts of other things that we know about, retinal imaging, skin characteristics, that we don't actually have any systematic way of measuring in the clinic. So the last couple of minutes, I'm going to tell you about the Apple Heart and Movement study, which has 14 independent sensors of the watch. This was a watch-dependent study. There's obviously a ton of additional information from the phone. We also are able, in about 10% of the 200-patient cohort, 200-subject cohort, to be able to get a ton of data from their health record upload. One of the other things that's worth pointing out about this study, and one of the reasons I love the Apple ecosystem, is it does allow you to annotate events at the wrist. So that actually turns out to be quite useful for all the reasons that you would imagine from my perturbation response characteristic. What's possible, we were able, because we have single lead ECGs in hundreds of thousands of people, we're able actually to build a massive data set, align all of their electrocardiograms, because they're all date and time stamped, and begin to build models of individuals, not just diurnal rhythm, but all of their low frequency data in almost every other setting that allows us to be able now to build mood parameters, to be able to build sun exposure, UV parameters. And this is only possible because of the fact that we have a high resolution physiologic data set. We were able to show during COVID, this was a perturbation that was, as I mentioned earlier, not anticipated when we started the study, but you can literally see how not only did study patterns, but study activity, but activity levels changed dramatically just on the date of the shutdown in March of 2020. The other things that are worth pointing out is that most of the existing data that are in the general medical literature are way off. So you can see here 70-year-olds who are achieving 210 beats a minute daily with exercise, and there are literally 10,000 of these in the study, that only a very small number of the lowest quartile of individuals are actually exercising at the traditional exercise thresholds that the medical profession recommends. We were able to show semi-continuous VO2 max and its responses to exercise. This is a model built on PPG and a variety of other inputs from the watch. And one of the things I want you to see here, because it shows you just how powerful VO2 max is, these are actually confidence intervals. These are 95% confidence intervals. So if you look, basically, you can almost perfectly predict. This is one of the reasons why everybody thinks VO2 max is a great predictor of age. Well, it turns out it's because it directly correlates with age. It's almost a perfect predictor of longevity. And what it does tell you is that almost all of the potential for VO2 max is already present by the time you've completed your adolescent growth spurt. There are inverse relationships with almost everything you can imagine, all the musculoskeletal phenotypes. This is actually a very good predictor of frailty as well. This didn't come out very well, but one of the things that's most noticeable is it's almost impossible to change your VO2 max above the maximum that you had when you completed your adolescent growth spurt, no matter how much additional exercise you do. Here's another example of adding reference metadata. So many of you, if you have an Apple Watch, will know that there is a mindfulness app that actually has a breathing cycle in it. That is enough to organize all of your heart rate variability data. So it doubles the information content, allows you to predict diabetes, a host of other conditions. Again, unfortunately, the colors didn't come out very well in this, but all of the information content is roughly doubled by just adding that perturbation. We tried to do something very similar to some of the studies that Megan outlined with transvascular aortic valve replacement. We thought it was a very similar insult. It's all percutaneous. And what we found was that basically participation was the assay, that the best predictor of your mortality, morbidity was whether you were willing to wear the watch in the very first clinic visit. There's huge attenuation in many parts of these studies, but interestingly, if it's completely passive, it usually plateaus at about 30%. For things that require active involvement, like a survey, you can see we're down in 12 months, we're already below 40%. And so a lot of what I think you have to start to think about is how are you making this completely ambient or passive? I think interaction with patients other than real life stimuli is going to be very, very tough. Changing reserve is hard. This is a summary of the top studies out of 121 studies. And you can see there are only 3 or 4 studies down at the very bottom that actually have any impact at all on changing functional reserve. And those were all studies in much younger individuals. The majority of studies had almost no signal. And one of the other things that was interesting is socioeconomic status was also a predictor of whether there was even any signal at all. What we tried to do at the very end is to think about how we could map some of this tech onto biology. Most clinical biomarkers are like this. They're sort of very high level and generic. They don't have a ton of scalability. They're not mechanistically specific. So what you really want is something out here that has a huge dynamic range. I mentioned the unifying metadata that I like: time, chemical stimuli, and physical stimuli. So we actually did that outside the body with blood cells. We added small molecule perturbations, things that you would recognize, drugs, pH, you name it. And we were able to actually build a completely new set. You can see here just how dynamic these markers are. Here's one individual, no change with a small molecule. Here's another individual, a completely new set of cell populations arrives. And these are almost binary. We were able to find a completely new mechanism for thrombosis. We believe that in the long run, and we've started to build some of these tools, the way you really want to do it is to have it be part of all clinical care, so that every transaction, every exposure, every interaction with the patient is collecting data that helps to build a foundation model for their future. It's possible to do this. We have published a study, for example, with about 500 homeless people in Detroit with one of our companies, where we were able to show that by just closing, you can actually build reinforcement learning very effectively. The goal is ultimately to build these, as we heard earlier today, build these lifelong, personal, computable reserve trajectories. And ideally, what you want to do is to think about it so you have these huge populations where you can build massively sophisticated multi-billion feature LLMs or not LLMs, but real world models. And then you can fine tune those with deep phenotyping in much smaller cohorts, port things up and down. And that's, I think, how you're going to end up seeing all of this happen. So in summary, I apologize for going a little bit over. Multi-domain reserve is accessible and informative, but requires substantial scale and scope. No information content should be left behind. I think one of the problems we have is we tend to look under the light. Ambient sensing, closed-loop learning, and intervention will all be critical. That's how you understand how the system will work. Potential information content from wearables is largely untapped. We've just started doing a ton of work with keystroke data, for example, from watch and phone. And it's amazing how people's performance will change over time, just based on a whole host of metrics that you might not anticipate. Wearables offer fundamental infrastructure for personal data records, and I think that's ultimately how this is going to transform. Most of the information in your life is not in your health record, it's in your phone record or your television record, or what you put in the microwave. Another great advantage of working with companies that have a footprint in that space. And then to effect real change in any of these settings requires behavior modification, and that's probably the single most difficult thing to do. Thank a few people, Bruce Levy, Angela Splain, Max Aurelius, a whole team of people on the digital side and the funders, as you see, and thank you for your attention.
Take a couple of questions before we go for a break. Hopefully David has the mic somewhere. Or Suzanne. Okay, just hold on for a second. We'll go over here. Right over there. Just put your hand up for me. Yes.
I could say I'm...
So we need it for online folks for the stream. Thank you very much. So if you just say, so your name and affiliation. Thank you.
My name is Dr. Amate Sawicki. I'm a geriatrician from the New England Rec in the VA. My question is, what's your approach to defining reserve or resilience? Is it a standard deviation from the mean with all the data? Is it outcomes?
Outcomes. I mean, I actually think no concern is about how we think about it. The only way the patients care about it is actual outcomes. So the nice thing about this is I completely believe in the fact that the system that you're measuring reserve in has to be the same system you're measuring in the outcomes in. And that's the biggest problem, is that in medicine, everything happens, all the measurement is happening in a research setting, all the outcomes are happening in a clinical setting. And I think what you're going to see, and they're seeing it live, is as federal funding disappears, you're going to see compression of the two industries. There's no other industry where the R&D is separate from the actual deployment itself. And so one of the nice things about, for example, the Apple ecosystem is we're measuring only outcomes in the Apple system. So we're saying, okay, did you become diabetic? We know when they become diabetic. Did you fall? We know when you fell. Is your gait getting worse? Is your cognitive function getting worse? So you need those closed loops in order to be able to do anything. And anytime you're setting up some form of secondary system, you then are in deep trouble because you have to remap everything back onto the central core. So one of the nice things about these large ecosystems is they're effectively closed loops. And so that's how we see it. So we're literally counting bodies in a box, falls on the road, accidents on the highway. Those types of things end up being the outcomes that patients are interested in, and people who haven't yet become patients are interested in.
Hi, my name is David. I'm a physical therapist with Smart Moves PT. First of all, impressive presentation, especially on no sleep. I was surprised to hear about the mindfulness feature, making the rest of the watches metrics more accurate. Can you just explain?
It doesn't make them more accurate. It makes them reflect more directly on the underlying physiology. So, for example, if I measure your heart rate variability, I don't know if you just climbed stairs or if you just had a huge slug of coffee or if you are having the most stressful day of your life. The thing that mindfulness does, the thing that any organizing principle does, any metadata does, is it helps you structure something in a temporal domain and an amplitude domain in a way that allows you to get higher percentage of the information content out of the assay. This is why we do stress tests in cardiology. I don't know if your heart is short of blood if you're sitting in a chair. If you're able to walk 20 miles a day and then the following day you can only do 18, I know something likely changed to limit your functional capacity. So a lot of it is just understanding, as was just said in the last question, understanding what the outcomes are. And the reality is, when we measure outcomes in the system, if we use the data organized around mindfulness, because it has a breathing exercise that's calibrated in it for 60 seconds, that turns out to get rid of a lot of the sympathetic noise. You end up with almost all the parasympathetic data, which is the best predictor of all of these long-term outcomes.
Thank you. Is the Apple Heart study still ongoing, or is that?
Apple study, Heart and Move, there were 4 studies, and they've all condensed into one, so they're all now Apple Health. And that's the one that I was PI of the Apple Heart Movement study, and now I'm PI of the Apple Health study.
So we're going to take a brief break until 2:45. Let's thank Calum again.